Tonight, we're going to confront something that most people never think about. But once you understand it, you can never see reality the same way again. There are walls built into the fundamental structure of the universe. Not walls you can touch or see, but limits so absolute that nothing in existence has ever crossed them. Not light, not gravity, not time itself. These aren't engineering problems waiting for better technology. They're deeper than that. They're written into the mathematics of space-time, woven into the structure of every particle and every force. And here's what makes it truly unsettling. If any one of these limits could be broken, even by the smallest amount, reality itself would become logically impossible. Cause and effect would collapse. Information would destroy itself. The universe as we know it simply could not exist. Before we go any further, if this kind of deep exploration into how the universe actually works sounds like something you'd enjoy, a quick like or subscribe genuinely helps this channel keep going. It's a small thing, but it means a lot. Now, settle in and get comfortable as we explore where reality draws the line. Let's begin. Let's start with a question that sounds simple, but turns out to be one of the deepest questions in all of physics. What is a limit? Not a speed limit on a highway, not a boundary on a map, not a technological barrier that better engineering might someday overcome. A physical limit, a structural limit, a limit that is woven into the very mathematics that describe how the universe operates. Because that's what we're talking about tonight. We're talking about constraints that don't exist because our tools aren't good enough. They exist because the equations that govern reality say they must. And if those constraints were violated, even slightly, the equations wouldn't just give wrong answers. They would give impossible answers, contradictions, paradoxes, logical nonsense. The framework of physics would collapse from the inside. Think of it this way. In mathematics, you cannot divide by zero. It's not that mathematicians haven't tried hard enough. It's not that we need a better calculator. Division by zero is undefined because allowing it would make every number equal to every other number. 1 would equal 2, 5 would equal a billion. The entire structure of arithmetic would become meaningless. That's not a limitation of our ability. That's a limitation of logical consistency itself. The limits we're going to explore tonight are exactly like that, except they're built into the physical universe, rather than into abstract mathematics. They're the places where reality says, this cannot happen, not because it's difficult, but because allowing it would make everything else incoherent. And the first of these limits, the one that holds the entire framework of cause and effect together, is the speed of light. Now, you've heard about the speed of light before. You probably know it's fast. About 300,000 kilometers per second. You've probably heard that nothing can go faster. But what most people don't realize is that the speed of light is not really a speed limit in the way we normally think about speed limits. It's something much deeper than that. The speed of light is the rate at which causality itself propagates through the universe. It's the fastest rate at which any cause can produce any effect. It's not about light specifically. Light just happens to travel at this speed because photons have no mass. The limit would exist even if light didn't. It's built into the geometry of space-time itself. To understand why, we need to talk about something called Lorentz invariance. This is the mathematical symmetry that sits at the heart of Einstein's special theory of relativity. and it's one of the most precisely tested symmetries in all of physics. Lorentz invariance says something that sounds strange at first but turns out to be profoundly important. It says that the laws of physics are the same for all observers moving at constant velocities relative to each other, not just approximately the same, exactly the same. And one consequence of this symmetry is that the speed of light in a vacuum is identical for every observer, regardless of how fast that observer is moving. Let me explain why that's so strange. In everyday life, speeds add together. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing on the platform sees the ball moving at 120 kilometers per hour. This makes intuitive sense. It's how the world seems to work at the speeds we experience. But Einstein showed that this simple addition of speeds is only an approximation. It works well at low speeds, the speeds we encounter in daily life, but it breaks down as you approach the speed of light. If you're on a spacecraft moving at half the speed of light and you turn on a flashlight, you might expect that someone watching from outside would see the light moving at 1.5 times the speed of light. Your speed plus the light's speed. But that's not what happens. The light still moves at exactly the speed of light, not 1.5 times. Exactly 1 times 300,000 kilometers per second. Both you on the spacecraft and the person watching from outside measure the same speed for that light beam. This seems impossible. How can both observers measure the same speed when one of them is already moving at half the speed of light? The answer is that space and time themselves adjust to keep the speed of light constant. This is not a metaphor. It's not an approximation. Space literally contracts in the direction of motion, and time literally slows down for the moving observer. These adjustments are precisely described by a mathematical expression called the Lorentz factor. The Lorentz factor is usually written as 1 divided by the square root of 1 minus v squared over c squared, where v is the velocity of the moving object and c is the speed of light. At everyday speeds, this factor is so close to 1 that you'd never notice the difference. If you're driving a car at 100 kilometers per hour, the Lorentz factor is 1.00000000000005. The difference from 1 doesn't show up until the 15th decimal place. Your clock runs slower than a stationary clock by an amount so tiny it's completely undetectable, but as velocity increases toward the speed of light, this factor changes dramatically. At 50% of the speed of light, the Lorentz factor is about 1.15. Time is running about 15% slower for the moving observer compared to a stationary one. Distances are contracted by the same factor. At 90% of the speed of light, the Lorentz factor jumps to about 2.3. Time is running less than half as fast. 99% of light speed, the factor reaches about 7.1. At 99.9%, it's about 22.4. And as velocity approaches exactly the speed of light, the Lorentz factor doesn't just get large, it goes to infinity. That's not a figure of speech. The mathematics are explicit. As v approaches c, the denominator of the Lorentz factor approaches 0, and 1 divided by something approaching 0 approaches infinity. Time dilation becomes infinite, length contraction becomes total, and the energy required to continue accelerating becomes unbounded. This is where the limit becomes absolute. To accelerate any object that has mass to exactly the speed of light would require infinite energy. Not a lot of energy. Not more energy than we currently have available. Infinite energy. The entire energy content of the observable universe would not be enough, because infinite means without limit. There is no finite amount of energy, no matter how large that would suffice. The mathematics simply do not permit it. This is what makes the speed of light fundamentally different from every other speed limit you've ever encountered. A highway speed limit is enforced by laws and police. You can break it if you choose to accept the consequences. The sound barrier was once thought to be unbreakable, but it was an engineering problem, not a fundamental one. Chuck Yeager broke it in 1947 by flying fast enough. But the speed of light is not an engineering problem. It's a mathematical wall. The equations of special relativity, which have been confirmed by every experiment ever conducted, say that reaching the speed of light requires infinite energy. And infinite energy does not exist in a finite universe. There's no cleverness that gets you around this. There's no trick. The mathematics close the door completely. But the real question is, why does this limit exist? Why should there be a maximum speed at all? What would go wrong if you could exceed it? The answer takes us into the deepest consequence of the speed of light limit, which is its role in preserving causality. Causality is the principle that causes precede their effects. You throw a ball, then it hits the wall. You flip a switch, then the light turns on. You send a message, then someone receives it. This ordering, cause before effect, is not just a habit of human perception. It's a structural feature of how events relate to each other in space-time. In special relativity, whether two events happen in a definite order, one clearly before the other, depends on whether they could be connected by a signal traveling at or below the speed of light. If event A could send a light signal that arrives at event B before event B happens, then all observers in the universe agree that A happened before B. The ordering is absolute. It doesn't depend on who's watching or how fast they're moving. But here's the critical part. If two events are separated by a distance so large that even light couldn't travel between them in the time that elapses, then different observers can disagree about which event happened first. One observer might see event A happen before event B, while another observer moving at a different velocity might see event B happen before event A. Neither observer is wrong. Both are correct in their own reference frame. The ordering of those events is not absolute. It depends on the observer's motion. This is not a problem as long as no information passes between those events. If A and B can't influence each other, it doesn't matter which one happened first. There's no cause and effect relationship between them. They're independent events that just happen to occur in different places. But imagine what would happen if you could send a signal faster than light. Suppose you have some hypothetical device that transmits information instantaneously or at any speed greater than the speed of light. You send a message from event A to event B faster than light could travel between them. In your reference frame, A happens first, then B receives the message. Cause precedes effect. So far, no problem. But now consider an observer moving at high speed relative to you. Because A and B are separated by more distance than light could cross in the elapsed time, this second observer can legitimately see B happening before A. In their reference frame, the message arrived before it was sent. the effect preceded the cause. And if that second observer could also send faster than light signals, they could send a reply back to you that arrives before you sent the original message. You would receive an answer to a question you haven't asked yet. You could receive information from your own future. This doesn't just create a weird situation, it creates a logical contradiction. If you receive information from the future telling you the outcome of a decision you haven't made yet, you could use that information to make a different decision, which would change the outcome, which would change the information that was sent back, which would change your decision again. You get an infinite loop of contradictions. A causal paradox with no consistent resolution. This is not speculation. This is a mathematical theorem. It's called the Tolman paradox, or more precisely, it follows from the structure of Minkowski spacetime, the mathematical framework of special relativity. In this framework, any signal that travels faster than light in one reference frame can be shown to travel backward in time in another equally valid reference frame. This is not a matter of interpretation. It's a direct consequence of the Lorentz transformations, the equations that relate measurements between different observers. Faster than light signaling doesn't just break a speed record, it breaks causality itself. And causality isn't some optional feature of physics that you can turn off without consequences. Causality is what makes physics possible. Every physical law is a statement about how causes relate to effects. Newton's second law says that applying a force to an object causes it to accelerate. Maxwell's equations describe how changing electric fields cause magnetic fields, and vice versa. Quantum mechanics describes how the state of a system at one time determines the probabilities of outcomes at a later time. All of these laws assume that causes come before effects. Remove that assumption and every physical law becomes meaningless. You can't predict anything because effects might precede their causes. You can't explain anything because the causal chain that connects events would loop back on itself in contradictory ways. The speed of light isn't just a number, it's the structural boundary that keeps the universe logically consistent. Now, you might wonder, is all of this just theory? Is it possible that Lorentz invariance is just a very good approximation that breaks down at some extreme scale? The answer is no, at least not as far as any experiment has ever shown. Lorentz invariance is one of the most precisely tested principles in all of science. Let me give you a few examples. Particle accelerators routinely push protons and electrons to speeds exceeding 99.9999% of the speed of light. At the Large Hadron Collider at CERN, protons circulate at 99.999999% of the speed of light. Their Lorentz factor is about 7,461. Time runs over 7,000 times slower for those protons compared to clocks in the laboratory. Their effective mass energy is over 7,000 times their rest mass energy. And every single observation, every collision, every measurement at the Large Hadron Collider is perfectly consistent with Lorentz invariance. The equations of special relativity predict exactly what happens, down to extraordinary precision. If Lorentz invariance were even slightly wrong, if the speed of light limit could be exceeded even marginally, the results at particle accelerators would deviate from predictions. Particles would behave differently than the equations say. Energy wouldn't be conserved in the way we expect. None of that has ever been observed. Every experiment confirms the theory with breathtaking accuracy. Then there's GPS. The global positioning system relies on satellites orbiting Earth at about 14,000 kilometers per hour. That's fast, but it's only about 0.0013% of the speed of light. Even at this relatively modest speed, time dilation is measurable. The atomic clocks on GPS satellites tick slightly slower than identical clocks on the ground due to their velocity. There's also a competing effect from general relativity, where clocks tick faster in weaker gravitational fields, and the satellites are farther from Earth's center. The net effect is that GPS satellite clocks gain about 38 microseconds per day relative to ground clocks. That sounds tiny, but if this weren't corrected for, GPS positions would drift by about 10 kilometers per day. The fact that your GPS gives you accurate positions within a few meters is direct proof that relativistic time dilation is real and precisely described by the Lorentz transformations. There's another beautiful confirmation that comes from cosmic rays. When high-energy particles from deep space hit the upper atmosphere, they create showers of secondary particles, including muons. Muons are unstable particles with a mean lifetime of about 2.2 microseconds. Even traveling at close to the speed of light, a muon created at the top of the atmosphere should only travel about 660 meters before decaying. The atmosphere is many kilometers deep. Muons should never reach the ground, but they do. We detect muons at the surface all the time. The reason is time dilation. From our perspective on the ground, the moon is moving so fast that its internal clock runs slow. Its 2.2 microsecond lifetime, as measured by us, is stretched to many microseconds, long enough for the muon to traverse the atmosphere before decaying. From the muon's perspective, something equally strange happens. The muon's own clock runs normally, so it still decays in 2.2 microseconds. But from the muon's frame of reference, the atmosphere is length contracted. The distance it needs to travel is shortened, so it has enough time to reach the ground. Both perspectives are consistent, both give the same answer. The muon reaches the ground, and both rely entirely on Lorentz invariance being exactly correct. These aren't isolated examples. There are thousands of experimental confirmations from nearly every branch of physics. Nuclear physics, atomic physics, particle physics, astrophysics, condensed matter physics. Lorentz invariance shows up everywhere, and it has never been violated. Not once in over a century, of increasingly precise measurements. Some physicists have even searched specifically for tiny violations of Lorentz invariance, looking for cracks in the symmetry that might hint at deeper physics. These experiments, some of which are sensitive enough to detect deviations at the level of 1 part in 10 to the power of 33, have found nothing. The symmetry holds perfectly as far as we can tell. This brings us back to the central idea. The speed of light is not a speed limit in the ordinary sense. It's not like a wall that something fast might crash into. It's a structural feature of space-time geometry. It arises from the Lorentz symmetry of the universe, a symmetry that determines how space and time relate to each other, how energy and momentum transform between observers, and how cause and effect maintain their ordering across the cosmos. Violating this limit wouldn't just mean going fast. It would mean breaking the causal structure of the universe. Effects would precede causes. Paradoxes would become physical realities. The entire framework of predictive physics would collapse. And that's why it cannot be done. Not because we lack the technology, because logic itself forbids it. Let me be clear about something, because this is a point that often gets confused. When physicists say nothing can go faster than light, they don't mean that no object has ever been observed going faster than light, and maybe someday one will be. They mean that the mathematical structure of our best and most thoroughly tested theories of physics makes faster than light propagation of information logically inconsistent with causality. It's not an empirical gap waiting to be filled. It's a structural impossibility within the framework, the same way dividing by zero is a structural impossibility within arithmetic. Could the framework itself be wrong? In principle, yes. All scientific theories are provisional, but replacing special relativity would require a new theory that explains every experiment special relativity already explains, all thousands of them, while also allowing for faster than light travel without destroying causality. No such theory exists. No proposed modification of physics has come close to achieving this. Every attempt to build a consistent theory that permits faster than light information transfer has either failed mathematically or reduced to something equivalent to special relativity in the domains where we can test it. There's a subtlety worth mentioning here. The expansion of the universe can carry galaxies apart at effective speeds greater than light speed. Distant galaxies are receding from us faster than light due to the expansion of space itself. But this doesn't violate the speed of light limit because no information is being transmitted. Those galaxies aren't moving through space faster than light. Space itself is expanding between us and them. No signal, no cause, no effect is traveling faster than light. The causal structure of the universe remains intact. Similarly, in quantum mechanics, entangled particles appear to influence each other instantaneously across any distance. When you measure one particle, the other seems to instantly adopt a correlated state. But again, no information is transmitted. You cannot use entanglement to send a message faster than light. The correlations only become apparent when the two observers compare the results, which requires a conventional signal traveling at or below light speed. Quantum entanglement respects the speed of light limit at the level that matters, the level of information and causality. The universe is remarkably careful about this. It allows all sorts of strange and counterintuitive phenomena, expanding space, quantum entanglement, virtual particles popping in and out of existence, but it never, under any circumstances, allows a cause to follow its own effect. That boundary is absolute. That line is never crossed. And the speed of light is the gatekeeper. So here's where we stand. The speed of light is not just fast. It's the speed of causality. It's the rate at which the structure of cause and effect propagates through the fabric of space-time. It's enforced by Lorentz invariance, a symmetry so deeply embedded in the architecture of physics that violating it would not just break one law, it would break the logical consistency of all laws simultaneously. It has been tested to extraordinary precision and never found wanting. It is, as far as we can tell, absolute. And this is just the first limit. The universe has others. Limits that govern how precisely reality can be known, how cold matter can become, how much information a region of space can hold. Each one is enforced by a different piece of the mathematical framework. Each one would create paradoxes or logical contradictions if it were violated. And together, they don't just constrain reality, they define it. They tell us not just what the universe does, but what the universe is. Because a universe without limits isn't a universe of infinite possibility. It's a universe of infinite contradiction. And contradiction is the one thing that cannot exist. We've just seen how the speed of light acts as an absolute wall, protecting the causal structure of the universe. Nothing with mass can reach it. No information can exceed it. And if anything could, cause and effect would collapse into paradox. That limit lives at the scale of the very large, governing how events relate to each other across the vast distances of space-time. But now we're going to descend in the opposite direction. We're going to go small, unimaginably small. We're going to explore what happens when you try to look at reality at its most fundamental level, at the level of individual particles, at distances so tiny that they make atoms look like galaxies. And what we're going to find is another limit, a different kind of wall, one that doesn't prevent you from going too fast, but prevents you from knowing too much. This is the Heisenberg uncertainty principle, and it is profoundly, fundamentally misunderstood by almost everyone who has heard of it. Most people think the uncertainty principle is about measurement. They think it says something like, when you try to measure a particle, you disturb it, so you can't know everything about it at once. This sounds reasonable. It sounds like a practical limitation. Like if you try to measure the temperature of a cup of coffee by sticking a cold thermometer into it. The thermometer changes the temperature slightly, so your measurement is never perfectly accurate. And yes, there is something called the observer effect in quantum mechanics, where measurement does disturb a system. But that's not what the uncertainty principle is about. Not really. The uncertainty principle is much deeper than that. It doesn't say we can't measure a particle's position and momentum at the same time because our instruments are too clumsy. It says the particle does not have a definite position and a definite momentum at the same time. Those properties literally do not simultaneously exist with precise values. It's not that we're ignorant of the values, it's that there are no values to be ignorant of. Let me say that again because it's important. The uncertainty principle does not describe a limitation of human knowledge. It describes a limitation of physical reality. The blur is not in our eyes, it's in the universe itself. To understand why, we need to go into the mathematical heart of quantum mechanics. In quantum theory, every physical quantity you could measure, position, momentum, energy, spin, is represented by a mathematical object called an operator. An operator is not a number. It's more like a set of instructions that acts on the quantum state of a particle and produces possible measurement outcomes. The operator for position tells you about where the particle can be found. The operator for momentum tells you about how it's moving. Now, in ordinary arithmetic, it doesn't matter what order you multiply numbers. 3 times 5 is the same as 5 times 3. This property is called commutativity. Multiplication of ordinary numbers is commutative. But the operators in quantum mechanics are not ordinary numbers. And for certain pairs of operators, the order absolutely matters. When you apply the position operator followed by the momentum operator to a quantum state, you get a different result than if you apply the momentum operator followed by the position operator. The difference between these two orderings is not zero. It's a specific fixed value related to Planck's constant, the fundamental constant of quantum mechanics. This mathematical property is called non-commutativity, and it is the actual source of the uncertainty principle. The fact that position and momentum operators do not commute is not a feature of any particular experiment or measurement device. It's built into the algebraic structure of quantum mechanics itself. It's a mathematical theorem, provable from the axioms of the theory, that if two operators don't commute, then no quantum state exists in which both quantities have simultaneously precise values. The product of their uncertainties must always be greater than or equal to a specific minimum value, which is Planck's reduced constant divided by 2. This is Heisenberg's uncertainty relation. The uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to Planck's reduced constant divided by 2. It's not an inequality about measurement error. It's an inequality about the fundamental nature of quantum states. It says that reality itself is structured in such a way that certain pairs of properties cannot both be sharp at the same time. Let me make this concrete. Imagine you have an electron and you want to know exactly where it is. In principle, you can prepare the electron in a quantum state where its position is extremely well defined. You can localize it to a tiny region of space. But the mathematics of quantum theory guarantee that when you do this, the electron's momentum becomes wildly uncertain. It could be moving in almost any direction at almost any speed. The more precisely you pin down where the electron is, the less defined its motion becomes. And this is not because your measurement kicked the electron and gave it a random push. It's because a quantum state that has a sharp position simply does not have a sharp momentum. The two properties are complementary. They trade off against each other not as a matter of practicality, but as a matter of mathematical structure. The same works in reverse. If you prepare the electron in a state with very well-defined momentum, so you know very precisely how fast it's moving and in what direction, then its position becomes maximally spread out. The electron could be found almost anywhere. It's not that you lost track of where it went, it's that it genuinely does not have a specific location. The quantum state that describes a particle with precise momentum is a wave that extends across all of space. The particle is, in a very real sense, everywhere at once. This trade-off is exact. It's quantitative. It's described by a precise mathematical inequality. And it's governed by Planck's constant, a number with a definite measured value of approximately 6.626 times 10 to the negative 34 joule seconds. This constant sets the scale at which quantum effects become important. For objects much larger than atoms, the quantum uncertainties are so tiny relative to the object's size and momentum that they are completely undetectable. A baseball has a position uncertainty so small that it would take longer than the age of the universe to notice the blur. That's why the everyday world seems perfectly definite and classical. Quantum uncertainty is always there, but for macroscopic objects, it's vanishingly small. For subatomic particles, however, Planck's constant is significant. Electrons, protons, photons, all of these exist in a regime where the uncertainty principle dominates their behavior. You cannot describe an electron as a tiny ball sitting at a specific point in space with a specific velocity. That picture is wrong. An electron is described by a wave function, a mathematical object that encodes the probabilities of finding the electron in various positions and with various momenta. The wave function doesn't describe our ignorance. It describes reality. The electron genuinely exists in a spread out, probabilistic state until a measurement forces it to reveal a specific value. Now, there's another form of the uncertainty principle that leads to even stranger consequences. Position and momentum aren't the only conjugate pair. Energy and time are also related by an uncertainty relation. The uncertainty in a system's energy multiplied by the uncertainty in the time over which that energy is measured must also be greater than or equal to Planck's reduced constant divided by 2. The interpretation of this relation is slightly different from the position-momentum version, because time in quantum mechanics is not an operator in the same way that position is, but the physical consequences are real and measurable. One of the most dramatic consequences is the existence of virtual particles. The energy-time uncertainty relation says that for extremely short durations of time, the energy of a system can fluctuate by a correspondingly large amount. The shorter the time interval, the larger the allowed energy fluctuation. For incredibly brief moments, enough energy can appear from nothing to create particle-antiparticle pairs, which then annihilate each other and disappear before the fluctuation can be directly observed. These are called virtual particles, and they're not just theoretical constructs. They have measurable effects. The Casimir effect is one of the most famous demonstrations. If you place two uncharged metal plates extremely close together in a vacuum, they experience a tiny but measurable force pushing them together. This force arises because the virtual particles, or more precisely the quantum fluctuations of the electromagnetic field, between the plates are constrained by the boundary conditions. Fewer fluctuation modes can fit between the plates than exist in the open space outside. The imbalance creates a net force. This effect has been measured experimentally and matches the theoretical predictions with high precision. The Lamb shift is another example. In the hydrogen atom, quantum vacuum fluctuations cause a tiny shift in certain energy levels that classical physics and even basic quantum mechanics can't explain. This shift, first measured by Willis Lamb in 1947, is precisely predicted by quantum electrodynamics, the quantum theory of light and matter which fully accounts for the effects of virtual particles. There's another consequence of the uncertainty principle that's even more dramatic than vacuum fluctuations: quantum tunneling. Imagine a particle trapped behind an energy barrier, like a ball sitting at the bottom of a bowl with walls. It doesn't have enough energy to climb over. In classical physics, the ball stays in the bowl forever. It doesn't have enough energy to escape, so it can't escape. End of story. But in quantum mechanics, the particle's position is not perfectly defined. Its wave function doesn't stop abruptly at the wall of the barrier. It extends into and through the barrier, decaying exponentially but never quite reaching zero. And if the barrier is thin enough, the wave function emerges on the other side with a small but non-zero amplitude. This means there's a real probability that the particle will suddenly appear on the other side of the barrier without ever having had enough energy to climb over it. It doesn't go over the barrier, it doesn't go around it. It passes through it, as if the barrier weren't entirely there. This is not theoretical speculation. Quantum tunneling is measurable and happens constantly throughout the universe. The sun shines because of quantum tunneling. Inside the sun's core, hydrogen nuclei must overcome an enormous electromagnetic repulsion to fuse together. The thermal energy in the core is not sufficient for the nuclei to classically overcome this barrier. But tunneling allows them to pass through it at a rate that sustains the fusion reactions powering the sun. Without the uncertainty principle, without tunneling, the sun would not burn, stars would not shine, and we would not exist. Radioactive decay is also a tunneling phenomenon. An alpha particle inside a heavy nucleus doesn't have enough energy to escape the nuclear force binding it, but its wave function extends beyond the nucleus, and occasionally the particle tunnels out, producing the radioactive emissions we detect. The scanning tunneling microscope, one of the most important instruments in nanotechnology, directly exploits tunneling to image surfaces at the atomic level. Quantum tunneling is the uncertainty principle made visible, and it shapes the universe at every scale. These phenomena reveal something astonishing about the nature of empty space. A perfect vacuum, a region with no particles and no radiation, is not truly empty. It's seething with quantum fluctuations. Virtual particles are constantly appearing and disappearing, energy is fluctuating up and down, fields are vibrating at every point. The vacuum is the lowest energy state, but the uncertainty principle guarantees that this lowest energy is not zero. There's always some residual activity, some irreducible quantum noise. True nothingness, perfect stillness and emptiness, is forbidden by the commutation relations of quantum field theory. Emptiness itself has a limit it cannot cross. All of this leads to a natural question. If we keep going smaller, if we look at shorter and shorter distances and shorter time intervals, where does it end? Is there a smallest possible distance, a shortest possible time, a floor below which the concept of measurement itself stops making sense? The answer is yes, and it's called the Planck scale. The Planck scale is where the two great pillars of modern physics, quantum mechanics and general relativity, crash into each other. Quantum mechanics governs the very small, describing the behavior of particles and fields. General relativity governs gravity, describing the curvature of spacetime caused by mass and energy. For most situations, you only need one of these theories. Quantum mechanics works beautifully for atoms and particles. General relativity works beautifully for stars and galaxies and the large-scale structure of the universe. But at certain extreme conditions, you need both simultaneously. And when you try to use both at the same time, the mathematics begins to break down. The Planck length is approximately 1.6 times 10 to the negative 35 meters. To appreciate how small this is, consider that a proton, which is already incredibly tiny, has a diameter of about 10 to the negative 15 meters. The Planck length is 20 orders of magnitude smaller than a proton, 20 powers of 10. That's the same ratio as between a grain of sand and the diameter of Earth. And the Planck length is that much smaller than something that's already vanishingly tiny. If an atom were the size of the observable universe, the Planck length would still be far smaller than any object in our everyday experience. The Planck scale is not merely small in the way that atoms are small. It exists at a level of tininess that has no meaningful analogy in human experience. It's not just small, it's unfathomably, ridiculously, almost meaninglessly small. The Planck time is the time it takes light to travel one Planck length. That's approximately 5.4 times 10 to the negative 44 seconds. This is so short that every event you've ever experienced, every thought you've ever had, every process in every star in every galaxy, all of it unfolds over durations that are incomprehensibly long compared to the Planck time. These values aren't arbitrary. They emerge naturally when you combine three fundamental constants: the speed of light from special relativity, the gravitational constant from general relativity, and Planck's constant from quantum mechanics. There's only one way to combine these three constants to get a quantity with the dimensions of length, and the result is the Planck length. There's only one way to get a quantity with the dimensions of time, and the result is the Planck time. These scales are not chosen by convention. They're dictated by the structure of the theories themselves. So what happens at the Planck scale? Why is it a limit? The answer comes from a collision between two principles. From quantum mechanics, the uncertainty principle tells us that probing very small distances requires very high energies. This is because of the position-momentum uncertainty relation. To localize a measurement to a tiny region of space, you need a probe with a very short wavelength, which means very high momentum, which means very high energy. The smaller the distance you want to probe, the more energy you need. This is why particle accelerators are so large. The Large Hadron Collider, with its 27-kilometer ring, accelerates protons to enormous energies, specifically so they can probe distances down to about 10 to the negative 20 meters. To probe even smaller distances, you'd need even higher energies. Let me walk you through what happens as you try to probe smaller and smaller distances. Imagine building a series of increasingly powerful particle accelerators, each one designed to look at shorter distances than the last. Your first accelerator probes distances of about 10 to the negative 15 meters, roughly the size of a proton. This requires particle energies of about 1 billion electron volts, which is what accelerators achieved decades ago. It revealed the internal structure of protons and neutrons, showing that they're made of quarks. You build a more powerful accelerator. Now you're probing 10 to the negative 18 meters, 1,000 times smaller than a proton. This requires energies in the range of 1 trillion electron volts, which is roughly what the Large Hadron Collider achieves today. You see the fundamental forces operating at this scale, confirming the standard model of particle physics. You push further. 10 to the negative 21 meters. 10 to the negative 24 meters. Each step requires 1,000 times more energy than the last. The accelerators become enormous. The energy densities become extreme. But so far, the physics holds. You keep seeing structure at smaller scales. Now you push toward 10 to the negative 30 meters. You're getting close to the Planck length. The energy required is becoming astronomical. You're concentrating more and more energy into a smaller and smaller collision volume. And something new starts to happen. The energy density in your collision region is becoming so intense that spacetime itself begins to curve appreciably. The region you're trying to probe is developing significant gravitational effects. You push further. 10 to the negative 33 meters. Now the gravitational effects are dominant. The energy you're pumping into your measurement is curving space-time so strongly that the collision region is approaching the conditions for black hole formation. And then, at the Planck length, 10 to the negative 35 meters, you cross the threshold. The energy required to resolve that distance, concentrated into a region that's small, exceeds the Schwarzschild limit. A black hole forms. Your probe particle, your target, your measurement apparatus, everything within that region disappears behind an event horizon. The measurement destroys itself. The distance you were trying to probe is now hidden inside a black hole and is fundamentally inaccessible. Now, from general relativity, we know that energy curves space-time. Mass and energy are sources of gravity. If you concentrate enough energy into a small enough region, you create such extreme curvature that a black hole forms. The boundary of a black hole, called the event horizon, is a region from which nothing can escape, not even light. And once a black hole forms, anything inside it is cut off from the rest of the universe. You can't get information out of a black hole through classical means. Here's where the two principles collide. As you try to probe shorter and shorter distances, you need higher and higher energies concentrated in smaller and smaller regions. At some point, the energy you're pumping into your measurement becomes so large and so concentrated that it creates a black hole. And once a black hole forms, it swallows your measuring apparatus, your probe particle, and any information about the distance you were trying to measure. The measurement becomes impossible, not because your instruments aren't good enough, but because the act of measuring at that scale destroys the thing you're trying to measure. The distance at which this happens is precisely the Planck length. Below the Planck length, the energy required to probe that scale exceeds the threshold for black hole formation. You literally cannot look at distances shorter than the Planck length, because any attempt to do so creates a gravitational singularity that hides the very thing you're trying to observe. This is not a technological limitation. It's not that we need better microscopes or more powerful accelerators. It's a fundamental clash between the two deepest theories we have. Quantum mechanics demands that probing small distances requires high energy. General relativity demands that sufficiently high energy in a small region creates a black hole. Together they establish a floor, a minimum meaningful length, below which the concept of distance itself becomes incoherent. Think about what that means. We're not saying that space might continue below the Planck length, but we just can't see it. We're saying that the very question, what happens at distances shorter than the Planck length, may not have a meaningful answer. It's like asking what's north of the North Pole. The question uses familiar words in a grammatically correct sentence, but it doesn't point to anything real. The concept of direction north doesn't extend past the pole. Similarly, the concept of spatial distance may not extend below the Planck length. Our current understanding of physics simply has no coherent description of sub-Planckian distances. The same logic applies to Planck time. You can't have a meaningful time interval shorter than the Planck time because the energy fluctuations required during such an interval would again create black holes. Time, like space, appears to have a minimum meaningful resolution. Below the Planck time, the concept of before and after may not apply. The sequential ordering of events that we take for granted may dissolve into something we don't yet have the mathematical tools to describe. This is where theoretical physics hits its current frontier. We have quantum mechanics, which works beautifully down to about the scale of atomic nuclei. We have general relativity, which works beautifully at all scales larger than the Planck scale. but we do not have a consistent quantum theory of gravity, a theory that properly merges quantum mechanics and general relativity into a single framework that works at the Planck scale. String theory, loop quantum gravity, causal set theory. These are all attempts to build such a framework, but none has been experimentally confirmed. We're stuck, in some sense, looking at the Planck scale from the outside, knowing that something important happens there, but unable to see exactly what. What we can say with confidence is that the Planck scale represents a structural limit. It's not a wall built by our ignorance. It's a wall built by the intersection of two fundamental theories. Quantum mechanics says small distances require high energy. General relativity says high energy in small regions creates black holes. Together, they establish a minimum scale below which measurement, distance, and time lose their conventional meaning. Let me bring this back to the big picture. We've now seen two fundamentally different kinds of limits. The speed of light is a limit on the rate of causal propagation, enforced by Lorentz invariance. The uncertainty principle is a limit on the precision of physical properties, enforced by the commutation relations of quantum operators. And the Planck scale is a limit on the resolution of space and time, enforced by the collision between quantum uncertainty and gravitational collapse. Each of these limits is structural. None of them are about what we can or cannot do. They're about what reality can or cannot be. The speed of light isn't a barrier we haven't broken yet. It's the speed at which causality operates, and exceeding it would create logical paradoxes. Quantum uncertainty isn't a flaw in our instruments. It's a feature of the algebraic structure that governs all physical quantities at the quantum level. The Planck scale isn't a resolution we haven't achieved. It's the point where the two deepest theories of physics make further resolution incoherent. And notice something else. These limits are connected. The speed of light appears in both special relativity and in the definition of the Planck scale. Planck's constant appears in both the uncertainty principle and the Planck scale. The gravitational constant connects the Planck scale to general relativity. These aren't separate, independent walls placed at random locations throughout physics. They're interlocking features of a single framework. The same constants show up again and again, linking the limits together into a coherent structure. This coherence is what makes these limits so compelling. They don't feel arbitrary. They feel architectural, like the load-bearing walls in a building. You might wish you could remove a wall to make a room bigger, but if that wall is holding up the floor above, removing it wouldn't give you more space. It would bring the whole building down. The speed of light holds up causality. Quantum uncertainty holds up the stability of atoms and the structure of matter. The Planck scale holds the boundary between physics we understand and physics we don't yet have the language to describe. Remove any one of them, and the entire structure of physical law becomes inconsistent. There's one more thing I want you to understand before we move on. These limits are not restrictions on an otherwise limitless reality. They are reality. The uncertainty principle doesn't prevent particles from having definite properties. It tells us what particles actually are, probabilistic entities described by wave functions. The Planck scale doesn't hide a deeper layer of smaller distances. It marks the point where distance as a concept breaks down. The speed of light doesn't frustrate our desire to go faster. It defines the geometric structure of the space-time we exist in. When you look at a diamond, you see a beautiful, rigid, transparent crystal. Its beauty comes from its structure, from the precise arrangement of carbon atoms locked in a tetrahedral lattice. That structure is what makes a diamond a diamond. It's not a constraint imposed on the carbon atoms from outside. It's what the carbon atoms are doing. The limits of physics are like the structure of a diamond. They're not constraints imposed on reality from outside. They are what reality is doing. They define the structure. And without that structure, there would be no physics. No matter, no stars, no planets, no life, no minds to wonder about any of it. We've descended from the cosmic scale of causality and light speed down to the subatomic realm of quantum uncertainty and the Planck flaw. We've found walls at both ends. At the large scale, causality cannot be violated. At the small scale, reality cannot be resolved beyond a certain point. These walls are not barriers blocking our progress. They're the bones of the universe. They hold everything together. And we're about to discover that the universe has still more limits. Limits that govern not just speed and precision, but temperature, disorder, and the very nature of information itself. We've now encountered two walls built into the structure of reality. The speed of light prevents causality from breaking. The uncertainty principle prevents physical properties from being simultaneously precise beyond a fundamental limit. The Planck scale prevents space and time from being meaningful below a certain resolution. These limits operate at the extremes of speed and smallness. But now we're going to explore a limit that operates everywhere, at every scale, in every process, in every corner of the universe. A limit that governs not what things are made of or how fast they can go, but how they change, how they evolve, how they move from one state to another. We're going to talk about temperature, about entropy, and about the deepest constraints that thermodynamics places on what the universe can and cannot do. And it starts with a number. 0. Specifically, 0 Kelvin. Absolute zero. Negative 273.15 degrees Celsius. The lowest temperature that can exist. Temperature, at its most fundamental, is a measure of the average kinetic energy of the particles in a system. When something is hot, its atoms and molecules are moving fast, vibrating intensely, bouncing off each other with tremendous energy. When something is cold, those motions slow down. The particles move more sluggishly, vibrate less, carry less energy. Temperature is motion at the microscopic scale, and absolute zero is the point where, classically speaking, all that motion would stop. Every atom, every molecule, perfectly still. No vibration, no kinetic energy, nothing moving at all. But here's the thing, you can't get there. And this isn't a statement about our refrigeration technology being insufficient. It's not that we need better cooling systems. It's a fundamental law of physics, as inviolable as the speed of light or the uncertainty principle. The third law of thermodynamics, sometimes called the Nernst-Planck statement, says that it is impossible to reduce the temperature of a system to absolute zero in a finite number of steps. You can get close, you can get extraordinarily close. Laboratories have cooled matter to within billionths of a degree above absolute zero, but you can never reach it. Each successive step of cooling removes less and less energy. The closer you get to absolute zero, the harder it becomes to extract the remaining thermal energy. Each step brings you closer, but the steps become progressively smaller, like walking toward a wall where each stride covers only half the remaining distance. You keep getting closer, but you never arrive. Reaching absolute zero would require either an infinite number of cooling steps or a single step that extracts an infinite amount of entropy from the system. Both are physically impossible. This isn't merely a practical obstacle. The mathematics of thermodynamics makes it structural. As a system approaches absolute zero, its entropy, which is a quantity we'll discuss in depth shortly, approaches a minimum value. For a perfect crystal, this minimum is zero. But achieving exactly zero entropy would require a process that perfectly orders every single particle in the system, removing every last trace of thermal randomness. The amount of work required to accomplish this final ordering diverges. It grows without bound, just as the energy required to accelerate a massive object to the speed of light diverges to infinity. The work required to cool a system to exactly absolute zero diverges to infinity. The structure of the equations forbids it, and there's a deeper reason, one that connects directly to what we discussed earlier. Even if you could somehow extract all the thermal kinetic energy from a system, even if every atom were brought to a classical standstill, quantum mechanics would step in and say no. Remember the uncertainty principle. The position and momentum of a particle cannot both be precisely defined at the same time. If a particle were perfectly still, its momentum would be exactly zero. That's a perfectly precise value. But the uncertainty principle demands that if momentum is precisely known, position must be completely uncertain. The particle could be anywhere. Conversely, if you confine a particle to a specific location, like an atom locked in a crystal lattice, it must have some residual momentum, some irreducible jitter, some minimum kinetic energy that can never be removed. This minimum energy is called zero-point energy. It's the lowest possible energy a quantum system can have, and it's not zero. It's a small but definite amount of energy dictated by Planck's constant and the confinement of the particle. Even at absolute zero, particles would still vibrate. They would still move, not because they're warm, but because the commutation relations of quantum mechanics forbid perfect stillness. True motionlessness would require a particle to have simultaneously precise position and zero momentum, and that would violate the uncertainty principle. So absolute zero is unreachable for two independent reasons that reinforce each other. The third law of thermodynamics says you can't get there in finite steps, and quantum mechanics says that even if you could, you wouldn't find stillness waiting for you. There's always motion, there's always energy, the floor is real, and it's higher than zero. This is a limit of the same character as the ones we've already seen. It's not about what we can't do. It's about what reality can't be. A universe at absolute zero, with every particle perfectly motionless, is inconsistent with the mathematical structure of quantum theory. It can't exist. The equations won't allow it. Now let's pivot to something that might seem like a completely different topic, but is actually deeply connected. Entropy. If absolute zero is the floor of temperature, entropy is something even more fundamental. It's a limit that governs the direction of all physical processes, the direction of time itself. Most people have heard that entropy is a measure of disorder. And that's not wrong exactly, but it's a simplification that misses the real power of the concept. Entropy, in its proper definition, is a measure of the number of microscopic configurations that are consistent with the macroscopic state of a system. Let me unpack that because it's crucial. Consider a box of gas. From a macroscopic perspective, you can describe the gas by a few numbers: its temperature, its pressure, its volume. These are measurable quantities that tell you about the gas as a whole. But at the microscopic level, the gas is made of individual molecules, billions upon billions of them, each with its own position and velocity. There are an enormous number of different ways those molecules could be arranged and still produce the same temperature, pressure, and volume. Each specific arrangement of all the molecules, every position and every velocity of every single particle is called a microstate. The macroscopic description, temperature and pressure and volume, is called a macrostate. Entropy measures how many microstates correspond to a given macrostate. This definition comes from Ludwig Boltzmann, one of the founders of statistical mechanics. Boltzmann's famous equation, engraved on his tombstone, states that entropy equals Boltzmann's constant multiplied by the natural logarithm of the number of microstates. It's one of the most important equations in all of physics. And what it tells us is that entropy is fundamentally about counting. It's about how many different microscopic arrangements are compatible with what you observe at the large scale. A low entropy state is one where relatively few microscopic arrangements would produce the observed macroscopic properties. Think of a perfectly organized room where every book is on the shelf, every item is in its designated place. There are very few ways to arrange the objects and still have the room look organized. A high entropy state is one where a vast number of microscopic arrangements would produce the same macroscopic appearance. Think of the same room after an earthquake, books everywhere, items scattered randomly. There are countless ways the objects could be arranged and still look like a mess. A mess is high entropy not because some force pushes things toward disorder, but because there are overwhelmingly more messy configurations than tidy ones. And this is where the second law of thermodynamics comes in. The second law states that the total entropy of a closed system can never decrease over time. It can stay the same, or it can increase, but it cannot go down. Entropy always increases. This law is often presented as if it were some mysterious cosmic mandate, some deep force that pushes the universe toward disorder. But when you understand Boltzmann's definition, the second law becomes almost obvious. It's about probability. Pure, simple probability. Imagine you have a box divided in half by a partition. All the gas molecules are on the left side. The right side is empty. This is a low entropy state because the molecules are confined to half the box. There's only a relatively small number of microstates, where all molecules are on the left. Now you remove the partition. What happens? The molecules spread out. They fill the entire box. This is a high entropy state because now the molecules can be anywhere in the box, and there are vastly more microstates where the molecules are spread throughout the whole volume than microstates where they're all on one side. How vastly more? Let's think about it. For a single molecule, after removing the partition, there's a 50-50 chance it's on the left side or the right side. The probability that it's still on the left is 1/2. For two molecules, the probability they're both still on the left is 1/2 times 1/2, which is 1/4. For 10 molecules, it's 1/2 to the 10th power, about 1 in 1,000. For 100 molecules, it's 1/2 to the 100th power, which is about 1 in 1,000,000 trillion. For a mole of gas, which contains about 6.02 times 10 to the 23rd molecules, the probability that all molecules would spontaneously end up on the left side is 1/2 raised to the power of 600 billion trillion. This number is so unimaginably small that it has more zeros after the decimal point than there are particles in the observable universe. This is why entropy increases. It's not enforced by a law in the way that we usually think of physical laws. It's enforced by statistics, by the sheer, overwhelming, crushing weight of probability. High entropy states are simply more probable than low entropy states by factors so large that the distinction between incredibly unlikely and impossible becomes meaningless. In any realistic scenario with any macroscopic number of particles, entropy will increase because there are astronomically more ways for it to be high than to be low. The system doesn't need to know about the second law. It just explores its available microstates randomly, and by pure chance, it ends up in a higher entropy state because there are so many more of them. Could entropy decrease? In principle, for a small system over a short time, tiny fluctuations can temporarily decrease entropy slightly. And indeed, the fluctuation theorem in statistical mechanics quantifies exactly how likely such decreases are. For systems of a few particles, they happen occasionally. But for macroscopic systems, for anything you can see with your eyes or hold in your hands, a significant decrease in entropy is so improbable that it would never happen in the entire lifetime of the universe. Not once. Not if you waited a trillion years. The numbers are simply too large. So the second law of thermodynamics is, in a sense, the most statistically robust law in all of physics. It doesn't rely on any particular force or interaction. It doesn't depend on whether you're dealing with gas molecules, photons, electrons, or stars. It follows purely from the mathematics of large numbers. Any system with many degrees of freedom that evolves according to time-symmetric microscopic laws will, with overwhelming probability, move toward higher entropy. This is essentially a theorem of mathematics applied to physics. Now, what would it mean if this limit could be violated? What if entropy could systematically decrease in a closed system? The consequences will be staggering. First and most practically, a decrease in entropy would enable perpetual motion machines. A perpetual motion machine of the second kind is a device that converts heat entirely into work without any other effect. The second law forbids this because converting heat into work requires a temperature difference, and the process of extracting work from that difference always increases the total entropy of the system and its surroundings. If you could decrease entropy, you could create a machine that runs forever, extracting unlimited energy from the thermal energy of its environment. You could power a city by cooling down the ocean by a fraction of a degree. You'd have infinite free energy. This sounds wonderful until you realize what it would mean for the consistency of physics. Energy conservation, the first law of thermodynamics, would remain technically intact. You wouldn't be creating energy from nothing. You'd be converting thermal energy into useful work with perfect efficiency. But the statistical framework underlying all of thermodynamics would collapse. Every prediction made by statistical mechanics, every calculation of chemical reaction rates, every understanding of phase transitions and heat engines and stellar evolution, all of it would be wrong. The mathematical framework that successfully predicts the behavior of everything from refrigerators to neutron stars would be internally inconsistent. Second, and more subtly, a systematic decrease in entropy would reverse the thermodynamic arrow of time. In physics, the fundamental laws at the microscopic level are time symmetric. The equations governing particle interactions work equally well forward and backward in time. If you filmed two particles colliding and played the film in reverse, the reverse collision would also obey the laws of physics. There's nothing in the microscopic laws that distinguishes past from future. And yet, at the macroscopic level, time clearly has a direction. Ice melts but doesn't spontaneously freeze. Eggs break but don't unbreak. Coffee cools down but doesn't spontaneously heat up by absorbing energy from a colder room. This macroscopic direction of time, the arrow of time, comes from the second law. Entropy increases toward the future. That's what distinguishes the past from the future at the macroscopic scale. The past had lower entropy. The future has higher entropy. Our entire experience of time's flow, of before and after, of causes leading to effects in the everyday world, is grounded in this statistical asymmetry. If entropy could decrease, the arrow of time would reverse. Effects could precede causes at the macroscopic level. Broken eggs could reassemble. Information that was erased could spontaneously reappear. Memories could form of events that haven't happened yet. The entire structure of macroscopic causality, which we spent so much time exploring earlier in the context of the speed of light, would be undermined from a completely different direction. The speed of light protects causal ordering at the level of spacetime geometry. The second law of thermodynamics protects causal ordering at the level of statistical mechanics. Both limits serve the same deep function, maintaining the logical consistency of the cause-effect relationship that makes physics possible. There's a third consequence that's particularly striking. Information, in the physical sense, is intimately connected to entropy. This connection was established by Claude Shannon in his mathematical theory of communication, and deepened by physicists like Rolf Landauer and Charles Bennett. The essential insight is that erasing one bit of information, flipping a known value to an unknown one, necessarily increases the entropy of the environment by, at least Boltzmann's, constant times the natural logarithm of 2. This is called Landauer's principle, and it has been experimentally verified. Let me make this concrete because Landauer's principle sounds abstract, but it has real, measurable consequences. Every computer you've ever used obeys it. When your computer erases a bit of data, when it overwrites a 1 with a 0 or clears a register in the processor, it must dissipate a minimum amount of energy into the environment as heat. That minimum is Boltzmann's constant times, the temperature of the environment times the natural logarithm of 2. At room temperature, that works out to about 3 times 10 to the negative 21 joules per bit erased. This is an incredibly tiny amount of energy. Modern computers dissipate far more than this per operation because they're not operating anywhere near the thermodynamic limit. The excess heat comes from inefficiencies in the circuit design, resistance in the wiring, and other engineering factors. But no matter how efficient you make a computer, no matter how perfectly you engineer every transistor and every wire, you can never erase information without paying at least this minimum thermodynamic cost. In 2012, A team of physicists in France directly measured Landauer's limit for the first time. They used a tiny silica bead trapped by a laser beam as a 1-bit memory system and carefully measured the heat dissipated when the bit was erased. The result matched Landauer's prediction precisely. Information erasure has a minimum thermodynamic cost. This is not engineering. This is physics. The universe charges a fee for forgetting, and that fee is paid in entropy. The implication is profound. Information is physical. It's not an abstract concept floating above the material world. It's encoded in the physical states of matter and energy, and manipulating it has thermodynamic costs. Erasing information produces heat. Copying information requires energy. And the second law guarantees that the total amount of useful information in a closed system can never spontaneously increase. You can't create information from noise without doing work. If entropy could decrease in a closed system, this relationship would break. Information could spontaneously appear from nowhere. Random noise could organize itself into meaningful data without any input of energy or work. A blank hard drive could spontaneously fill with coherent information. A scrambled message could unscramble itself. The distinction between signal and noise, between meaningful data and random static, would dissolve. This might sound like science fiction, but the consequences for physics would be devastating. Every computation, every measurement, every observation depends on the reliability of the relationship between information and entropy. If that relationship could be violated, the concept of measurement itself would become unreliable. You couldn't trust the readings on your instruments because the instrument's stored information could spontaneously change. Science as a practice depends on the second law being true. Let me connect this back to the other limits we've discussed. The speed of light limit is enforced by the geometry of spacetime, specifically by Lorentz invariance. The uncertainty principle is enforced by the algebraic structure of quantum mechanics, specifically by the non-commutativity of operators. What enforces the second law of thermodynamics? The answer is probability theory applied to systems with many degrees of freedom. But this isn't as separate from quantum mechanics as it might seem. In quantum statistical mechanics, entropy is defined in terms of the density matrix of a quantum system, and the second law can be derived from the unitarity of quantum evolution. Unitarity means that quantum evolution preserves the total probability of all possible outcomes. It's the quantum mechanical version of saying that information is conserved. Unitary evolution guarantees that if you start with a certain amount of quantum information, you end with the same amount. You can shuffle it around, transform it, spread it out, but you can't create it from nothing and you can't destroy it. This connects the second law to one of the deepest principles in quantum mechanics. The increase of thermodynamic entropy in a closed system is fundamentally linked to the fact that quantum mechanics is unitary. Violating the second law would require violating unitarity, which would mean that probabilities no longer add up to 1. Outcomes could appear or disappear. The mathematical framework of quantum theory would become inconsistent. So the second law of thermodynamics is not merely an empirical observation about how gases behave or engines run. It's connected to the deepest structural features of quantum theory. The commutation relations that give us the uncertainty principle, the unitarity that preserves quantum information, and the statistical weight of Microstates that drives entropy increase are all part of the same mathematical framework. Pulling out the second law would unravel quantum mechanics along with it. Let me give you one more perspective on why the entropy limit is so absolute. Consider the entire observable universe as a closed system. The universe began in an extremely low entropy state shortly after the Big Bang. The cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space, is remarkably uniform, with temperature fluctuations of only about 1 part in 100,000. This uniformity represents an extraordinarily special, low entropy configuration for the gravitational field. Since then, entropy has been increasing. Stars formed, nuclear reactions occurred, heat flowed from hot regions to cold regions, structures developed, and the total entropy of the universe has been climbing steadily. The current entropy of the observable universe is dominated by the supermassive black holes at the centers of galaxies. The entropy of the supermassive black hole at the center of the Milky Way alone is vastly greater than the entropy of all the stars and gas and radiation in the galaxy combined. We'll return to black hole entropy shortly because it leads to the deepest limits of all. But for now, the point is that the universe has a thermodynamic history. It started low and it's been climbing. And this climb is irreversible on any practical timescale. In the far future, the universe will approach a state of maximum entropy. Stars will burn out. Black holes will slowly evaporate. All temperature differences will equalize. The universe will become a vast, uniform, featureless expanse of extremely low energy radiation spread evenly across space. No structure, no gradients, no ability to do work. This is sometimes called the heat death of the universe, but the heat death doesn't happen all at once. It unfolds in stages, each one unimaginably longer than the last. First comes the end of the stellar era. In roughly 100 trillion years, all the hydrogen and helium in galaxies will be consumed. The last stars will sputter out. The final red dwarfs that burned their fuel so slowly they lasted trillions of years, and the universe will go dark. No new stars will form because there's nothing left to form them from. What remains are stellar corpses, white dwarfs, neutron stars, and black holes drifting through an expanding void. The white dwarfs will slowly cool over quadrillions of years, radiating away their residual heat until they become black dwarfs, cold and invisible, barely above the temperature of the surrounding space. Neutron stars will do the same, cooling into inert spheres of degenerate matter. The black holes will be the last objects with significant entropy, but even they are not eternal. Through Hawking radiation, a process we'll discuss shortly, black holes slowly lose mass and energy. The smallest ones evaporate first. Stellar mass. Black holes take roughly 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies will take far longer, roughly 10 to the power of 100 years. But eventually, even they vanish in a final burst of radiation. After that, there is nothing left but a thin, cooling soup of photons, neutrinos, and perhaps some scattered elementary particles, all slowly spreading through an ever-expanding void. No temperature differences, no gradients, no capacity for work, no possibility of change. It's not a dramatic event. It's the quietest possible ending, a slow, inevitable slide into perfect equilibrium where nothing ever changes again. because there's no thermodynamic driving force left to cause change. This future is the ultimate expression of the second law. Entropy always increases, structure always degrades, useful energy always dissipates into useless heat. And this isn't because some destructive force is tearing things apart. It's because there are overwhelmingly more ways for energy to be spread out than for it to be concentrated. More ways for things to be disordered than ordered. More microstates at high entropy than at low entropy. The universe is simply exploring its available states. And the vast majority of those states look like equilibrium. The heat death of the universe is as inevitable as a ball rolling downhill, except the hill isn't made of gravity. It's made of probability. And the ball is the entire cosmos. So where are we now? We've seen 4 limits. The speed of light protects causality. It's enforced by Lorentz invariance. The uncertainty principle sets a floor on how precisely conjugate physical properties can simultaneously exist. It's enforced by the commutation relations of quantum operators. The Planck scale sets a floor on the resolution of space and time. It's enforced by the collision between quantum mechanics and general relativity. And the laws of thermodynamics, both the unattainability of absolute zero and the relentless increase of entropy, are enforced by the statistical structure of quantum mechanics, the positivity of zero-point energy, and the unitarity of quantum evolution. Each of these limits is different. They govern different things: speed, precision, resolution, temperature, disorder. But they share a common character. None of them are technological barriers. None of them are engineering problems waiting for a solution. Each one is a structural feature of physical law, built into the mathematics, woven into the equations. Violating any one of them wouldn't just break a single rule. It would create internal contradictions that would collapse the entire framework of physics. And there's one more limit to discuss, perhaps the deepest of all. A limit that governs not particles or temperatures or speeds, but information itself. A limit that connects gravity, quantum mechanics, and thermodynamics into a single astonishing statement about the nature of reality. Involves black holes, surfaces, and the startling possibility that everything you see around you, every object, every person, every star, might be a projection from a 2-dimensional boundary at the edge of the cosmos. We've traveled through 3 layers of limits built into the fabric of reality. The speed of light holds causality together. The uncertainty principle and the Planck scale set a floor beneath which physical properties and space-time itself lose coherent meaning. Thermodynamics forbids absolute zero and demands that entropy always increases, establishing an irreversible direction to every process in the universe. Each of these limits is structural, mathematical, and absolute. But now we're going to confront the deepest limit of all. A limit that doesn't govern how fast things move, how precisely they can be known, or how cold they can get. This limit governs how much can exist. How much information, how much complexity, how much physical reality can be packed into a given region of space. And what it reveals about the architecture of the universe is genuinely shocking. To get there, we need to start with a question that sounds almost philosophical, but turns out to have a precise physical answer. Is there a maximum amount of information that could be contained in a finite region of space? The answer is yes, and the limit is called the Bekenstein bound. In the early 1970s, a young physicist named Jacob Bekenstein was thinking about black holes. At the time, black holes were understood through the lens of general relativity. They were regions of space-time where gravity was so strong that nothing could escape, not even light. The boundary of a black hole, the event horizon, was considered a point of no return. Anything that fell past it was lost forever. Black holes were thought to be perfectly simple objects, described entirely by just three properties: their mass, their electric charge, and their angular momentum. Nothing else. No texture, no internal structure, no complexity. This was known as the no-hair theorem. A black hole has no hair. It's featureless, smooth, completely characterized by three numbers. But Bekenstein realized this created a serious problem with the second law of thermodynamics. Imagine you have a box of gas with a certain amount of entropy, a certain number of microscopic configurations. Now you throw that box into a black hole. The gas, along with all its entropy, disappears behind the event horizon. From the outside, the entropy is gone. It's been swallowed. If the black hole itself has no entropy, or very little, then the total entropy of the universe has decreased. The second law has been violated. This troubled Bekenstein deeply. The second law was one of the most robust principles in all of physics. It couldn't just fail because you tossed something into a black hole. There had to be something wrong with the picture. And what Bekenstein proposed was radical. He suggested that black holes do have entropy, enormous entropy, and that this entropy is proportional not to the volume of the black hole, but to the area of its event horizon. This was a stunning idea. Entropy, in every other context, scales with volume. If you have a box of gas and you double the volume, you roughly double the number of possible microstates, and the entropy increases accordingly. A bigger box means more ways to arrange the particles, which means more entropy. That's how entropy works for every normal physical system. But Bekenstein was saying that for a black hole, the maximum entropy is proportional to the surface area of its boundary, measured in fundamental Planck units. Not the volume enclosed, the area of the surface. A few years later, Stephen Hawking made this precise. Using a combination of quantum mechanics and general relativity, Hawking calculated the exact entropy of a black hole. The result, now called the Bekenstein-Hawking entropy formula, states that the entropy of a black hole equals its event horizon area divided by 4 times the Planck area. The Planck area is the Planck length squared, about 2.6 times 10 to the negative 70 square meters. This is an incredibly tiny unit of area, which means that even a modest-sized black hole has an unimaginably large entropy. To get a sense of scale, consider the supermassive black hole at the center of the Milky Way, Sagittarius A star. It has a mass of about 4 million times the mass of our Sun. Its event horizon has a radius of about 12 million kilometers. Its entropy, calculated from the Bekenstein-Hawking formula, is approximately 10 to the power of 90. That's a 1 followed by 90 zeros. For comparison, the total entropy of all the stars, gas, radiation, and ordinary matter in the observable universe, excluding black holes, is estimated at roughly 10 to the power of 88. The single supermassive black hole at the center of our galaxy has more entropy than all the non-black hole matter in the observable universe combined. And it's not even a particularly large black hole. The black hole at the center of M87 has a mass of 6.5 billion solar masses, and an entropy correspondingly larger still. But Hawking's contribution went beyond calculating entropy. He discovered something that shocked the physics community. Black holes are not truly black. They radiate. In 1974, Hawking showed that quantum effects near the event horizon cause black holes to emit a faint but steady stream of thermal radiation, now called Hawking radiation. The mechanism is rooted in the quantum vacuum fluctuations we discussed earlier. Near the event horizon, virtual particle-antiparticle pairs are constantly forming and annihilating. Normally, these pairs appear and disappear harmlessly. But at the edge of a black hole, something different can happen. One member of the pair can fall behind the event horizon, while the other escapes into space. The escaping particle carries positive energy away from the black hole. Conservation of energy demands that the particle swallowed by the black hole must effectively carry negative energy, reducing the black hole's total mass. Over time, this process slowly shrinks the black hole. It loses mass, it loses energy, it evaporates. For large black holes, this process is extraordinarily slow. The temperature of Hawking radiation is inversely proportional to the black hole's mass. A stellar mass black hole has a Hawking temperature of about 60 billionths of a Kelvin, unimaginably cold, far colder than the cosmic microwave background radiation that fills the universe. Such a black hole gains more energy from absorbing background radiation than it loses through Hawking emission. It actually grows, but in the far future, as the universe expands and cools, the background temperature will eventually drop below the Hawking temperature of even the largest black holes. At that point, evaporation will dominate. The black hole will slowly shrink over timescales that dwarf the current age of the universe. And this leads to one of the deepest unsolved problems in theoretical physics: the black hole information paradox. When matter falls into a black hole, it carries information with it. Information about its quantum state, its composition, its history. If the black hole eventually evaporates completely through Hawking radiation, and that radiation is purely thermal, meaning it carries no information beyond its temperature, then where did the original information go? It seems to have been destroyed. But quantum mechanics, as we discussed, is unitary. Information cannot be destroyed. The total quantum information in a closed system must be preserved. So we have a direct contradiction between general relativity, which says information falls into the black hole and is lost when it evaporates, and quantum mechanics, which says information can never be lost. This paradox remains unresolved. Most physicists believe information is somehow preserved, encoded subtly in the correlations of the Hawking radiation through a mechanism we don't yet fully understand. Resolving the paradox will almost certainly require a complete theory of quantum gravity. It's one of the deepest hints we have that our current understanding of reality, as successful as it is still incomplete. Black holes are the most entropic objects in the universe. They are the maximum entropy configurations for a given region of space. And this leads directly to the Bekenstein bound. The Bekenstein bound states that the maximum entropy, and therefore the maximum information content, of any region of space is determined by the energy contained in that region and the size of the region. Specifically, the entropy is bounded by 2 pi times. the energy times the radius of the smallest sphere enclosing the region, divided by Planck's reduced constant times the speed of light. If you try to pack more information, more entropy, more physical complexity into a region than this bound allows, the energy density required will inevitably exceed the threshold for gravitational collapse. The region will form a black hole, and once a black hole forms, its entropy is given by the Bekenstein-Hawking formula, which depends only on the area of its event horizon. Let me make sure you grasp what this means. There is a maximum amount of information that can exist in any given volume of space, not a practical maximum, not a limit imposed by technology. A fundamental maximum imposed by the intersection of quantum mechanics, thermodynamics, and general relativity. You cannot encode more information in a region of space than the Bekenstein bound allows. If you try, gravity will step in and collapse the region into a black hole, which will then have exactly the maximum entropy allowed by its surface area. This is an extraordinary result. It connects three seemingly disparate branches of physics. Quantum mechanics contributes Planck's constant. Thermodynamics contributes the concept of entropy. General relativity contributes the physics of gravitational collapse, and together they produce a single, clean, inescapable limit on the information content of any region of space. But the truly startling implication is what the Bekenstein-Hawking formula says about where information lives. The entropy of a black hole scales with the area of its boundary, not the volume it encloses. This means the maximum information in a region of space is proportional to the surface area surrounding that region, not the volume inside it. If you have a sphere of space 10 meters in radius, the maximum information it can hold is not proportional to the volume of the sphere, which goes as the radius cubed. It's proportional to the surface area, which goes as the radius squared. As you make the region bigger, the maximum information grows more slowly than you'd expect. It grows with the square of the size rather than the cube. This is deeply counterintuitive. We live in 3 spatial dimensions. We expect information to fill a volume. If you have a library, the number of books it can hold depends on the volume of the building, not the area of its walls. If you have a hard drive, the amount of data it stores depends on the number of bits packed into its 3-dimensional interior. But the Bekenstein bound says that at the most fundamental level, the maximum information content of any region of space is determined by what's happening on its 2-dimensional boundary, not in its 3-dimensional interior. This idea, taken to its logical conclusion, leads to one of the most remarkable proposals in modern theoretical physics: the holographic principle. The holographic principle, proposed by Gerard 't Hooft and later refined by Leonard Susskind in the 1990s, states that all the information contained in any volume of space can be represented as information encoded on the boundary of that volume. The 3-dimensional interior is, in a precise physical sense, equivalent to a 2-dimensional description on the surface. Just as a hologram on a flat piece of film can encode a fully 3-dimensional image, the physics of a volume of space can be fully encoded on its 2-dimensional boundary. This is not a metaphor, it's not a loose analogy. In certain theoretical contexts, it has been made mathematically precise. The most famous example is the ADS/CFT correspondence, proposed by Juan Maldacena in 1997. This correspondence establishes an exact mathematical equivalence between a theory of gravity in a certain kind of curved spacetime called anti-de Sitter space, and a quantum field theory without gravity defined on the boundary of that spacetime. Every calculation you can do in the gravitational theory in the higher dimensional interior has a precise counterpart in the non-gravitational theory on the lower dimensional boundary, and vice versa. The two descriptions are completely equivalent. They're the same physics written in two different languages. The ADS/CFT correspondence has not been mathematically proven in the rigorous sense that a mathematician would demand, but it has passed every test that theorists have devised. Calculations done in the gravitational theory match calculations done in the boundary theory to extraordinary precision. Thousands of papers have explored its implications, and no inconsistency has been found. Most theoretical physicists working in this area consider it to be correct, or at least an extremely deep truth about the structure of physical theory. If the holographic principle is correct, then there is a fundamental limit not just on how much information can exist in a region of space, but on the nature of that information. The three-dimensional world we perceive, the world of depth and volume and spatial extension, may be a projection of a more fundamental two-dimensional description. The information that describes everything inside a region of space, every particle, every force, every interaction, all of it fits on the boundary surface, encoded at a density of no more than 1 bit per Planck area. Think about what this implies. The Planck area is incredibly tiny, about 2.6 times 10 to the negative 70 square meters. So the number of bits you can encode on the boundary of any macroscopic region is enormous. The boundary of a sphere 1 meter in radius can encode roughly 10 to the 70th power bits of information. That's vastly more than the information content of any computer system ever built or conceivable with current technology. In practice, we're nowhere near the holographic limit, but the limit exists. It's finite. It's determined by the surface area measured in Planck units, and if you try to exceed it, if you try to cram more information into the interior than the boundary can encode, you trigger gravitational collapse. A black hole forms, and the system reorganizes itself to respect the bound. The limit is self-enforcing. Gravity itself is the mechanism that prevents the information content of a region from exceeding what its boundary can describe. Now, I want to step back and connect all of this to everything we've discussed tonight, because the Bekenstein bound and the holographic principle aren't isolated curiosities. They're the culmination of all the limits we've explored, and they reveal how those limits fit together into a single coherent architecture. Start with the speed of light. The speed of light defines the causal structure of space-time. It determines which events can influence which other events. It creates the light cones that separate the causally connected from the causally disconnected. And it's the speed of light that determines the size of a black hole's event horizon for a given mass. The event horizon is defined as the surface from within which light itself cannot escape. Without a finite speed of light, there will be no event horizons, no black holes as we understand them, and no Bekenstein-Hawking entropy formula. The information bound depends directly on the causal structure that the speed of light creates. Then, the uncertainty principle. The Planck length and Planck time which set the minimum resolution of space and time, arise from the uncertainty principle's interaction with gravity. The Planck area, which is the fundamental unit of information density in the holographic bound, is the Planck length squared. The bit density on any surface is counted in Planck areas. Without the uncertainty principle, there would be no Planck scale, no minimum unit of area, and no quantization of the information capacity of surfaces. The holographic bound would have no natural unit to count in. Then, thermodynamics. The Bekenstein-Hawking formula is an entropy formula. It measures the number of microstates of a black hole. The entire concept of an information bound is a thermodynamic concept rooted in Boltzmann's statistical interpretation of entropy. The Bekenstein bound is the statement that the entropy of a bounded region cannot exceed a certain value. Without the second law, without the concept of entropy as counting microstates, the information bound would have no meaning. Every limit we've discussed feeds into the others. The speed of light creates causal structure and event horizons. The uncertainty principle creates the Planck scale and the minimum unit of information. Thermodynamics defines entropy and provides the framework for information bounds. General relativity provides the mechanism of gravitational collapse that enforces the bound. Quantum mechanics provides the microstate counting that gives the bound its meaning. Remove any single piece and the entire structure falls apart. This is why I said at the beginning that these limits are not separate barriers placed at random locations throughout physics. They're interlocking features of a single coherent framework. They depend on each other. They reinforce each other. They connect to each other through the fundamental constants, the speed of light, Planck's constant, Boltzmann's constant, the gravitational constant, that appear again and again throughout physics. Consider what this means. The universe isn't constrained by a collection of arbitrary rules imposed from outside. It's a self-consistent mathematical structure where every constraint follows from every other constraint. The speed of light limit implies the causal structure that makes event horizons possible. The uncertainty principle implies the Planck scale that quantizes information on those horizons. The laws of thermodynamics demand that entropy is well-defined and can never decrease. And the Bekenstein bound unifies all of these into a single statement about the maximum complexity of any region of space. Pull out one thread, and the entire tapestry unravels. This is what physicists mean when they talk about the deep structure of physical law. It's not a list of unrelated rules, it's a web of interconnected constraints that all support each other. The beauty of physics, the thing that makes physicists believe they're discovering something real and not just inventing convenient fictions, is this internal coherence. Every piece fits with every other piece. Every limit is consistent with every other limit. The whole thing hangs together in a way that would be extraordinarily unlikely if it were arbitrary. Let me address something that might be nagging at you. You might be thinking, these limits sound like they make the universe smaller, more restrictive, less interesting. Wouldn't a universe without limits be better? More possibilities, more freedom, more room for complexity and life and consciousness? The answer is no. And this is perhaps the most important insight of all. A universe without limits would not be a universe of infinite possibility. It would be a universe of infinite contradiction. And contradiction is not interesting. It's not complex, it's nothing at all. If the speed of light could be exceeded, causality would collapse. Effects could precede causes. You could change the past, but changing the past would change the present, which would change the decision to change the past, creating infinite loops of contradiction. No consistent history of events could exist. The universe wouldn't be richer for allowing faster than light travel. It would be logically impossible. There would be no coherent sequence of events to constitute a history. If the uncertainty principle could be violated, if particles could have simultaneously exact positions and momenta, the entire structure of quantum mechanics would collapse. Atoms would be unstable. Chemistry wouldn't work. The electron orbitals that give atoms their properties, that allow molecules to form, that make chemistry and biology possible, all of those are consequences of quantum uncertainty. Without the uncertainty principle, electrons would spiral into nuclei. Atoms would collapse. There would be no matter as we know it. If the second law of thermodynamics could be violated, if entropy could spontaneously decrease in closed systems, the arrow of time would dissolve. There would be no distinction between past and future. Processes could run forward or backward with equal probability. But without a direction of time, there would be no accumulation of complexity, no evolution, no development. Biological evolution requires irreversible chemical reactions. Memory requires irreversible changes in brain states. Thought itself requires a direction of time. Without the second law, consciousness as we understand it would be impossible. If the Bekenstein bound could be violated, if infinite information could be packed into a finite region, the consequences would be equally catastrophic. Gravitational collapse would be avoidable, meaning general relativity would be wrong. The connection between geometry and energy that defines gravity would break. The entire framework of spacetime would become inconsistent. In every case, removing a limit doesn't open up new possibilities. It destroys existing ones. It doesn't make the universe richer. It makes it incoherent. The limits are not cage bars restricting a free universe. They're the bones holding it up. Take them away and there's nothing left. This is the central insight of tonight's journey. The limits of physics are not obstacles. They're architecture. They're the structural features that make reality possible. A universe without the speed of light limit would have no consistent causal structure. A universe without quantum uncertainty would have no stable atoms. A universe without entropy increase would have no direction of time. A universe without information bounds would have no consistent geometry. Each limit enables something. Each constraint creates structure, and structure is what allows complexity and life and consciousness to exist. Think about music for a moment. A piano has 88 keys. That's a limit. You can't play a note between the keys. You're restricted to specific frequencies. And yet, within those constraints, every piece of music ever written for piano was composed. Mozart, Beethoven, Chopin, Debussy, every jazz improvisation, every pop song, every film score. The constraints don't limit the music, they enable it. Without the structure of defined notes and scales, you wouldn't have richer music. You'd have noise. The limits of physics work the same way. By forbidding certain things, contradictions, simultaneous precision, infinite information density, decreasing entropy, they create a framework within which extraordinary complexity can emerge. Stars can form and burn steadily for billions of years. Atoms can combine into molecules. Molecules can organize into living cells. Cells can evolve into organisms. organisms can develop brains, and brains can produce minds capable of understanding the very limits that made them possible. That last point deserves emphasis. You are sitting here, listening to this, understanding these ideas, because the limits of physics allowed you to exist. The speed of light gave the universe a consistent causal structure in which events could unfold in an orderly sequence. Quantum uncertainty gave atoms their stability and chemistry its richness. The second law gave time a direction, allowing complexity to build on itself, layer by layer, over billions of years. And the information bounds of the Bekenstein limit ensure that the physical world has a finite, describable, comprehensible structure rather than an infinite, incomprehensible chaos. You are the product of these limits, not despite them, because of them. Let me close with a thought about what all this might mean for the future of physics. We've discussed 4 categories of limits tonight. Causal limits enforced by relativity, precision limits enforced by quantum mechanics, thermodynamic limits enforced by statistical mechanics, and information limits enforced by the intersection of gravity, quantum theory, and thermodynamics. These limits are among the best tested and most deeply understood features of physics. They are not going away. No future theory will eliminate them, but a future theory might unify them. Right now, we don't have a complete quantum theory of gravity. We have quantum mechanics and we have general relativity, and they work beautifully in their respective domains, but they conflict at the Planck scale. The search for a theory of quantum gravity, whether it's string theory, loop quantum gravity, or something else entirely, is fundamentally a search for a framework that makes all of these limits consistent with each other at the deepest possible level. The holographic principle, the Bekenstein bound, the Bekenstein-Hawking entropy formula, these are clues. They tell us that gravity, quantum mechanics, and information theory are not separate subjects. They're aspects of a single underlying reality. A complete theory of quantum gravity would explain why the speed of light has the value it does, why Planck's constant has the value it does, why the gravitational constant has the value it does, and how all the limits we've discussed emerge from a single, unified mathematical framework. We don't have that theory yet. We might not have it for decades or even centuries, but every limit we've discussed tonight, every wall we've found, is a signpost pointed toward it. The limits of physics aren't just constraints on what reality can do. They're hints about what reality is. They're the fingerprints of a deeper structure that we can sense, but not yet see clearly. And the fact that these fingerprints are consistent, that they point in the same direction, that they fit together like pieces of a single puzzle, is one of the most compelling reasons to believe that such a deeper structure exists. The universe has walls, real, structural, mathematical walls that nothing has ever crossed and nothing ever will. The speed of light, the uncertainty principle, the Planck scale, absolute zero. The second law, the Bekenstein bound. These aren't limitations on human ambition. They're the deepest truths we've ever discovered about the nature of reality. They tell us that the universe is not a blank canvas where anything can happen. It's a precisely structured framework where only consistent things can happen. And within that framework, within those limits, the universe has produced stars and planets, oceans and atmospheres, cells and organisms, brains and minds, curiosity and wonder. Everything you've ever loved, Everything you've ever experienced, everything you are, exists because reality has walls it cannot cross. That's not a restriction. That's the deepest gift the universe has to offer. Structure, consistency. A framework in which something as improbable and beautiful as a conscious mind can emerge from unconscious matter and look up at the stars and ask why. The limits are the answer. They're what makes everything possible. The universe cannot go faster than light. It cannot know more than uncertainty allows. It cannot cool below absolute zero. It cannot reverse the flow of entropy. It cannot pack infinite complexity into finite space. And because it can't do any of these things, it can do everything else. It can build atoms. It can forge stars. It can create life. It can produce minds that wonder about their own existence. The deepest limits reality cannot cross are not barriers keeping us from a better universe. They are the reason there is a universe at all. And that, more than any single fact about speed or temperature or information, is the most profound discovery physics has ever made. Thank you for joining me on this journey tonight. Next time someone tells you about a limit, about something that cannot be done, remember what you've learned tonight. Not all limits are obstacles. Some of them are foundations. Some of them are the reason anything exists at all. Good night, and may you never look at the walls of reality the same way again.